So,
Oh,
howdy. So we are, let's see, what are we doing? What are we covering today? We're days 20,
25.
just 25.
Yeah, we did 24 on Friday.
Okay, so we got 25, and then we're at least going for the answers to 11. We'll see how we do on time, or is it 10?
11.
11. And then if we got time, we'll maybe hit another one. Well, actually, we might actually have time because 25 is a,
Yeah, it's short.
Part one.
yeah. So
All right.
without further ado, I will share my screen. Oh, I got a lot more screens today. Let's see. It's a gamble. I think it's this one.
So,
So did
most of us
anybody-
already finished 25 part 1.
Did anybody manage to save the Christmas?
Yeah.
We got to get all 50 stars, so none of us are there yet.
Yeah, not quite there yet.
We failed.
But yeah, but we do have one for part A. And so in order to do this, let's who wants to read this one today?
I can take this one.
All right, Scott, go ahead.
All right, well, this is the final puzzle for Advent of Code 2021, day 25, Sea Cucumber. This is it, the bottom of the ocean trench, the last place the sleigh keys could be. Your submarine's experimental antenna still isn't boosted enough to detect the keys, but they must be here. All you need to do is reach the sea floor and find them. At least you'd touch down on the sea floor if you could. Unfortunately, it's completely covered by 2 large herds of sea cucumbers. And there isn't an open space large enough for your submarine. Did you want to click on the sea cucumbers thing, or do we all know what they are?
I don't know what it
Click
is.
on it.
All right, let's see. Let's see these sea cucumbers.
They're echinoderms, right?
Oh, we cannot see.
Alex,
Did you
are
click?
Oh, let me see. Maybe it's following a window. Set up today.
Let's see. We're just waiting for the sea cucumbers.
It says my screen sharing is paused. Sorry for the technical difficulties, but for some reason my screen sharing has been paused. Let's go and see if I go back here.
But we still see your screen. That's weird.
I don't even know what I'm sharing anymore. You know, I'm going to stop and reshare because I have no idea. Oh, there's my screen. Oh, that's interesting. That's weird. I moved from one screen to the other.
Alex is using a different machine today, so things are a little bit strange.
Oh, it's strange indeed. Okay, so let's try resharing this one. Got that screen back.
Okay, I see your mouse pointer now, and we see the sea cucumbers.
All right.
They have quite a wide variety, it looks like, based on the pictures.
Yeah, I remember is one of the memorable words I had through biology was echinoderm. I don't know why, but
okay.
I really fixated on the word echinoderm, so I know that they were echinoderms.
Good memory.
But we eat them here in Asia, so a little bit more memorable, I guess, than other places where they're just a curiosity.
Yeah. I know in Korea we eat the gebu. Is that a type of sea cucumber?
I don't know.
The little pink ones that look like a part of a man's anatomy.
Oh no, those are those have their own thing.
Okay.
Because the sea cucumber, those like actually live like vertically, right, in the mud. Is that what you're talking about? The one that looks like a phallus?
Yeah. Yeah, I don't know how they live. I only see them in the fish tanks. They're just squirming around in the bottom.
Oh no, okay, I know what you're talking about. You're talking about the ones that look like bulbs.
I'm talking
It's like a flower bulb, but like a spiky flower bulb that like shoots out stuff. That might actually be a sea cucumber that you're talking about.
these ones.
Oh. No. I'm not sure what those are. They might be. I mean, they certainly look like they could be, but the echinoderm, I think Well, I guess they're usually spiky, which is I think the Echino and the Echinoderm,
Okay.
but I don't think they exclusively have to be spiky. I think it's just how they started out being named.
Interesting. Well, anyways, those are our sea cucumbers.
Yeah, this one's not, so maybe not.
Ah, that just looks like something you find in a toilet.
Yes. And in the wild, they sometimes look like that too until they move.
Okay. Very strange creatures.
Anyway, so we learned a little bit more about our.
All right, so there's two large herds of sea cucumbers on the bottom of the trench. And there isn't an open space large enough for your submarine, so we can't land our submarine. This seems like a big problem. Well, you suspect that the elves must have done this before, because just then you discover the phone number of a deep sea marine biologist on a handwritten note taped to the wall of the submarine's cockpit. Wait, so this is not the first time the elves have had this adventure? Have they lost the keys in this trench before? Let's see. I think we're going to call that phone number. Here we go.
They couldn't have given us the answers from the last years.
Yeah. Well, let's call this deep sea marine biologist. Sea cucumbers. Yeah, they're probably hunting for food, but don't worry. They're predictable critters. They move in perfectly straight lines, only moving forward when there's space to do so. They're actually quite polite. You explained that you'd like to predict when you could land your submarine. Oh, that's easy. They'll eventually pile up and leave enough space for, wait, did you say submarine? And the only place with that many sea cucumbers would be at the very bottom of the Mariana? You hang up the phone. I like the convenient hanging up of the phone right when we learn we're in the Mariana Trench. All
Yeah,
right.
you got the information you wanted. Don't need them anymore.
Yeah, we didn't care. We're not here for conversation. We got to save Christmas.
There you go.
All right, there are two herds of sea cucumbers sharing the same region. One always moves east, and they're marked with that little right-looking arrow, while the other always moves south, and they're marked with the down arrow, or V. Each location can contain at most one sea cucumber. The remaining locations are empty, marked with a period. The submarine helpfully generates a map of the situation, your puzzle input. For example, and we have a map here showing a lot of sea cucumbers. And some of them, you notice, that are marked with the V are the ones pointing south. And periods are empty spaces with no cucumbers. And the marks that are pointing to the right are the sea cucumbers in the herd that are facing east. And they can only move in the direction that they are facing. The east cucumbers only move east. The south cucumbers only move south. Wow, they're very one-directional creatures, I guess. Let's continue. Every step, the sea cucumbers in the east-facing herd attempt to move forward one location. Then the sea cucumbers in the south-facing herd attempt to move forward one location. When a herd moves forward, every sea cucumber in the herd first simultaneously considers whether there is a sea cucumber in the adjacent location it's facing, even another sea cucumber facing the same direction. And then every sea cucumber facing an empty location simultaneously moves into that location. All right, that was a lot of text. It just means that a sea cucumber can only move if at the beginning of the step, the space in front of him is empty. The space he wants to move into has to be empty at the beginning of his turn to move. And they go sequentially too. All of the eastern facing sea cucumbers move first, and then the south facing sea cucumbers move if they can. So in a situation like this, and we have an example here with three periods, and then 1, 2, 3, 4, 5 east facing sea cucumbers, and then 3 more periods. Well, after one step, only the rightmost sea cucumber would have moved. Yeah, because if we look at the top one, the sea cucumber on the very right has an open space in front of him. But all of the other sea cucumbers, they have a sea cucumber in front of them. The place they want to move is not empty, it's occupied. But that sea cucumber on the far right, he has an empty space in front of him, he can move. After the next step, 2 sea cucumbers move. All right, so now the sea cucumber farthest right can move again, and the sea cucumber behind him now has an empty space, so he can move too. During a single step, the east-facing herd moves first. Then the south-facing herd moves. So given this situation, and look carefully at the situation, we have 4 cucumbers here. We have, starting on the second row, we have an east-facing cucumber next to a south-facing cucumber. And farther in that row, we have a south-facing cucumber, and below him is an east-facing cucumber. So different cucumbers are blocked at different steps here. Let's see what happens. After a single step of the sea cucumbers on the left, only the south-facing sea cucumber has moved, as it wasn't out of the way in time for the east-facing cucumber on the left to move. All right, so we see that the east-facing one would have gone first, but because the south-facing one is blocking him, he can't move. So now it's the south-facing one's turn, and he has an empty space below him. He can move. So the east-facing one on the left side did not move, but the south-facing cucumber did. All right. But both sea cucumbers on the right have moved, as the east-facing sea cucumber moved out of the way of the right-facing south sea cucumber. So yeah, this eastern one, he moved first, he got out of the way. Now the southern one can move. So in one step, both of them were able to move. So remember, one of the key things here is that one step includes 2 sub-steps, I guess. First, the east-facing sea cucumbers move if they can, and then the south-facing sea cucumbers move if they can. And that's total, that is 1 step. And then we'd start again for step 2, the east-facing sea cucumbers would go again if they can, and then the south-facing ones. So let's continue. We have a little bit more to this question. Due to strong water currents in the area, sea cucumbers that move off the right edge of the map appear on the left edge, and sea cucumbers that move off the bottom edge of the map appear on the top edge. Sea cucumbers always check whether their destination location is empty before moving, even if that destination is on the opposite side of the map. Okay, so these sea cucumbers are like one of those really old Super Mario games from way back in the Nintendo era, where you go off the screen on the right and you teleport back to the left side. So you can just run endlessly and you're never going to go anywhere really. So the east-facing ones, yeah, if they go all the way off the right side, they teleport back to the first place on the left in their same row. Whereas the south-facing ones, they stay in their same column, but they go all the way down to the bottom, and after the bottom, they come back to the top of that same column. Okay, so they never disappear. We never get rid of any sea cucumbers. They just loop back to the beginning. All right, and then we have a nice example here that shows us an initial state with several cucumbers. We get the state after 1 step. I don't think we need to talk through all of these. We can just observe it by yourself, look through and see how they moved. And then it says, to find a safe place to land your submarine, the sea cucumbers need to stop moving. Again, consider the first example. And here's an example with quite a few different sea cucumbers. And we can see that they keep moving. Every step is a little bit different than the one before it. Some cucumbers move. We got steps 2, 3, 4, 5, and it keeps going. We have 10 steps, 20 steps, 30 steps, 40 steps, 50, 55, 56, 57, 58. And there we go. It says, in this example, the sea cucumbers stop moving after 58 steps. Wow, they moved a lot. But now after 58 steps, they are stuck. They can no longer move any further. They're kind of in a gridlock. Well, let's see then. Find somewhere safe to land your submarine. What is the first step on which no sea cucumbers move? All right, so that's what we got to do. We got to find out what step do the sea cucumbers stop moving. They can't move anymore for that step.
All right.
All right, that's an interesting one.
Cool, cool.
Is it 100
So?
by 100?
Yeah, how big is the actual input for this one? Mine was 137 by probably 137. At least 137 rows for mine. I can't count the columns as easily, but I'm guessing it's usually about the same. So a lot bigger than the sample input. But okay. So moving sea cucumbers. So we just have to, so you have to figure out which sea cucumbers can move, and then make sure to move them in the correct order. Make sure you're moving the eastern sea cucumbers first before you move the south facing sea cucumbers. And make sure that you're checking all of the locations kind of simultaneously. You don't want to make the mistake where there's two sea cucumbers next to each other and you move one, and then the other follows it in the same step. No, if they're next to each other, the second one would have to wait till the next step to move. Because at the beginning of that step, at the beginning of its turn, it's going to check whether it can move or not.
All right. Any other questions on this one?
I think this one's rather easy to understand.
Cool. So that is 25. That is the last day's puzzle.
Yeah.
Hopefully you guys enjoyed all the questions that we've covered so far, but we are now going to start going into the answers. So I think, from now on, our videos will only have answers, right? So let's see how many answers we can pack into a single session.
You know what? I've lost keys in the ocean before. I wonder if they ended up floating to the Mariana Trench.
Unless you're right over the Mariana Trench.
Probably not.
Submarine.
Yeah.
Well, I never found them, so they could have floated anywhere.
I suppose so. I suppose that's valid.
They could have gotten picked up by some, I don't know, crab submarines or something.
All right, so let's go into our answers. We're starting today with answers for 11, I believe.
All right, should we review the question?
Yeah, let's do that. So we'll reshare so we can rewind back to 11 to see what 11 was. Oh, the Dumbo octopuses.
Ah, yeah.
Yeah.
The flashing Dumbo octopuses.
Flashing Dumbo octopuses. So on this one, there's a grid of numbers you got to look at. All the grid of numbers, they advance by 1 on every turn. If any of them cross over 9 as they advance up in number, then they flash. Any octopus that flashes will cause their neighbors to also go up by 1. And if their neighbors go up by 1 and go beyond 9, they also flash, and so on. But you can only flash more than once, or at most once per step. So if for whatever reason they flash, they're not going to flash again if another neighbor flashes around them. And so it's kind of a chain reaction of flashing.
Yeah.
So that was the puzzle. And of course, our puzzle area was much larger than sample, but sample gives a pretty good indication as to what's going on. The final number is how many total flashes are there after 100 steps?
How many Dumbo octopuses have flashed?
It was a nice question.
Yeah.
Brain teaser.
So who wants to tackle it first?
Oh,
Can I go?
This is one of those interesting ones where our actual input is the same size as the sample input.
Oh, is that right?
Yeah, it was a 10 by 10 grid, I believe.
Oh, okay. My bad. I thought it's going to be another one of those where it
Yeah,
varied.
usually it is. So this one is a little bit unique.
So can I go first?
Sure.
The solution is in JavaScript for this one for me.
Is there a reason why?
So first, the main reason can be, I can say, debugging. I had a hard time in Python to set up my debugging.
Okay.
But in JavaScript, if you guys can see, I had already debugging set up, so it was really easy. It was really convenient to try with debugging. which I enjoyed. Next one could be, well, in Python, yeah, I had hard time to approach this problem actually.
Okay.
So
Well, now that
Maybe
you've
approached it in JavaScript.
now that you've done it in JavaScript, do you think you can rewrite it in Python?
yeah, that one I think I can, but I didn't have enough time.
Yeah. Okay.
But tomorrow's day 12, I'm thinking to do in both. But this one, I think once I got it in JavaScript, should be easy to implement in Python.
Okay.
So first, I'll go through my approach as usual. Can you guys,
Yep.
you guys can see my screen, right?
Yes.
Yeah.
So this is the grid we have, and the problem explains that every element in the grid improves by 1 on every step, and once we reach over 9, that element flashes, and that causes all of its neighbors to increment by 1, 2, and any of its neighbors go over 9, that neighbor also flashes, causing its neighbors to increment by 1, 2.
I think one key thing for this one is that I know previously when we had to consider neighbors, we ignored neighbors on the diagonals, but this one also includes diagonal neighbors, correct?
Yeah, so we have like 8 neighbors for every single, not every single, but at most we have 8 neighbors.
Right.
So we have 3 on the top. For this 5, we have 3 on the top, and we have 3 on the bottom here. We have 1 on the left and 1 on the right. Okay, my approach is I'm starting to loop through this matrix as usual, 1 by 1. And once I reach an element that will go over 9, I am starting my breadth first search using queue for graphs. So let's say this one is here was 9. So once I reach this one, I'll stop looping my initial matrix. From here, I will first flash my element, and once it flashes, I will start my breadth first search from one of its neighbors. So 1 by 1, I will start pushing its neighbors to my queue. All of them will be in my queue, and I will go on with my breadth first search. So 4 was pushed first, so I will take 4 and increment it. So if it goes over 9, in any case, if it goes over 9, I will push its neighbors to my queue. So it goes on. So in this case, it doesn't flash, so I just incremented all its neighbors 1 by 1. And let's say I have 9 here, and once I increment 6, I come to this 9, and it also flashes. In this case, I will start adding, or I will start pushing its elements or its neighbors to my queue too. So my queue, after the neighbors of my first element finishes, I'll go with neighbors of my second element and so on until my queue is empty. So once my queue is empty, which means I have incremented all its neighbors by 1, I will continue with my initial traversing of the matrix. So I'm using the queue-based BFS basically.
Okay.
Any questions? Clear? Right.
Yep.
Okay, so now is the code. So here I'm splitting it by line, and here I'm converting every element to integer. So at the end of this, I have a array inside an array, and inside array contains integers. And I don't have a file set up with Node.js. For this one, I'm just passing my input as a line of strings separate by a new line. So I'm splitting by a new line, and I'm looping through here and converting every element to integer. So I have a variable to keep track of my flashes. That's what we have to return. And I have my first loop, which is the number of the steps I have to loop through. So every time I flash an element, for every step, I am keeping that index so that I will not flash it again. So during one step, every item can flash only once. So this array is to keep track of my indices. I'm keeping track of them here as a string separated by comma. So my x and y has exactly like this here. So after that, this is the looping through the entire array, my matrix. So the horizontal line, my vertical line, here's the horizontal line, row. And every time I reach an element, I'm checking if it's less than 9, my current element, and it has not been flashed. Just in case I'm checking, this has not been flashed, so I will not increment. If it's not, if it has not been flashed and it's less than 9, I increment it by 9. And it is equal to 9. If it's equal to 9, first I will push it into my queue as the first element. And as long as my queue has elements inside it, which means its length is longer than or higher than 0, I will start my breadth first search. So I will take my first element from my queue and get its coordinates. Since it's a string separated by commas, I will get the elements separated by a comma and parse them to int. And first of all, I will flash it. If it is equal to 9, but I'm checking one more time. I think I had a reason there. I can't remember now, but I'm checking it one more time and setting it to 0, the current element. I'm increment by flash by 1. And here I will push it into my flashed array, the indexes, so I will not flash them again. And my neighbors array here, I will start pushing my neighbors into the array. As we have 8 neighbors maximum, but some cases like top corners, bottom corners, we have less than 8. In those cases, I'm using this approach. I remember Scott mentioned in the previous sessions.
Yeah.
So
with arrays.
yeah, before I had it set like this, undefined. Like I was just checking if it's not undefined, just like this. But in this case, some elements in my array have 0 in them, and 0 was also returning true, so I was not pushing them. So I had to manually check if they are not equal to undefined to take zeros also into account. So top row, bottom row, and the same row neighbors, if they are not undefined, I will push them my neighbors array, and these neighbors I will add to my queue and empty neighbors array, and so on. I will go with every element, and once I have gone through incrementing the neighbors, I will set my flashed, empty my flashed array because it's the next step now, and go on with my steps, the same process. So once my top loop is over, I will return the number of flashes I have. This is the part which is taking so many lines. I think adding those neighbors to my queue.
Yeah.
But the rest of it is simple. I have one queue and matrix traversal, matrix traversing. Yeah, that's about it.
Could you scroll down a little bit after that one? So you pull out of your queue and then scroll up.
Yeah.
Okay.
Here?
Yeah, so how do you make, well, so you revisit places you've already visited,
Yes.
which is fine. But
Yeah.
how do you know which ones have been, so you have this thing called flashed. When do you
Yeah.
check flash to make sure you don't reflash?
If they're equal to 9, but if they are not equal to 9, once they have been flashed, they are usually equal to 0, right? So
okay.
I do not
Gotcha.
really, yeah,
And that's
they are
the
equal
problem that
to,
you had with the 0 check and undefined because they've already flashed.
yeah. So I'm checking here, if they are not 9, they are less than 9. So in here, I'm checking before incrementing them by 1, I'm checking if they are not in my flashed array, so that I will not increment them if they have been flashed. If they have been flashed, I think they stay at 0
Yeah,
because they have spent all of the energy to flash, so they cannot go up anymore. So I'm checking here.
makes sense. Okay.
This part had me caught up yesterday, like it wasn't undefined, it was being set to 0, it was all working, was fine back then, but the numbers were less than the actual flashes, so it took me a while. That's fine.
That makes sense. Okay. Yeah. Cool.
It's good to see some more JavaScript too.
Yeah, I felt, I don't know, I had some, actually I didn't go through it, but my debugging environment for Python wasn't set, so I was in the dark most of the time how to debug. But on JavaScript it felt good, actually.
All right. Should I share mine now?
Sure.
All right, well, I did mine quite a bit different from Farouk. Let me show you. Can you see mine? All right, so I'll just start from the top. So Farouk already explained the question and how to check the neighbors and everything. So let me just share my code. So first, of course, like I always do, I could have done like Farouk with this one and just copied the input data straight into my file because it's a rather small one, only 10 lines. But since I am kind of stuck on using the file system reader, I just went with that way because I already have most of my functions set up in my template folder. Yeah, I created a template a long time ago with the basic files that I always use so that I can just copy and paste this into a new day. So in my template, I just have this for day 1, day 2, and then files for my sample and my input. So like always, I copied my template to start on this one. And that way I was able to just read my input file right away. I split it by line. So each line got its own new element in the array. And then I mapped through every element or every row and split it again by element. So each element here is its own thing. And then I converted every element into a number. So my final input array looks like this. So let me actually make it look nicer by getting that onto one row and get this onto one row. So it's an array of arrays of numbers. All right. And of course, it's longer than that. There's 8 more rows that are not showing right now. All right. Well, back to my code now. To start out, I knew that I needed a counter because I want to keep track of the number of flashes. So I actually don't like the name that I did this. I don't like naming it count. If I went back and redid it, I'd just change it to flashes or num flashes maybe to be a little bit more descriptive.
Global search and replace, man.
Yeah, I'm gonna make sure that I don't have any other things that are the same
That's a
name.
very
I might
common
have
word, though.
another flashes in here. And no, I guess I don't. I think on part 2, I do have a variable called flashes.
Hmm.
So anyway,
Yeah, you always want to be careful with global search and replace.
yeah, it looks like I'm safe on this one, but my code's not that long, so I'll just go through it. I'm gonna come back to my check neighbors function a little bit later. So I'll come back to that after I call it and let you know what's happening. So right now we'll skip that and we'll go on to my main loop. So like always, I don't know, I learned this trick from Marie to capture the length of the array that you're searching from if the length is not going to change. That way it doesn't have to do one extra calculation every loop just to calculate the length of the array. We can already set it. So now I'm going to loop through my array. I'm going to loop 100 times because that was part 1 of this question, was how many times have the octopuses flashed after 100 rounds or 100 steps. So we're going to do a 100 loop, and inside of there I have a couple different loops. So first I'm going to loop through every element in my array, and I'm going to increment every single element. So I have to have a nested loop here for each row, and then for each element in each row. I'm going to increment every element. Next, I did a second nested loop here. I have another I loop with a J loop inside. And in here, I'm going to check the neighbors if that element is greater than 9. So if during that initial increment, if it pushed the Dumbo octopus over 9, then I'm going to check its neighbors because that means it's going to flash. All right, and in my check neighbors function, I'm passing the coordinates, the row and the column for that Dumbo octopus. So let's go on to check neighbors. So in my check neighbors function, of course, I'm accepting my arguments for I and J. And then the first thing I'm going to do in here is I'm going to set that octopus who just flashed. So the octopus whose neighbors I am checking, I'm going to set that octopus to 0. He has just flashed, so I'm setting him to 0 now. And that'll come in handy a little bit later. So now I'm going to increment my counter because the octopus just flashed. So I'm going to add 1 to my counter. All right, now in order to make up the rest of my code a little bit cleaner and easier to work with, I created a neighbors array of objects in here. So this is all of my neighbors and their coordinates relative to the octopus that I'm checking. So the first row here is going to be the neighbor that's 1 row up and 1 element to the left. The next one is going to be the one up above. So 1 row up and directly above the current octopus. Next is the one up and to the right. Then I believe this one is going to be to the left of the octopus, to the right, to the bottom left, right below the octopus, and to the bottom right. So these are all of my neighbors, and this will allow me to loop through this array and use the I and J as keys in order to get the values here. So now I have a loop, and I set this loop as K because I'm already using I and J here. I don't want to get confused. So I have my K loop. I'm looping through my neighbors array. So I'm going to loop through here and check all of the neighbors. So to make things a little bit cleaner here, I initialized a new variable. I just set it as A because it didn't really need to be descriptive. It's just for convenience. I'm going to check. So A is going to be my neighbors of that row. So each row then during my loop. So for loop 1, this will be A. And now I can check if in my input, so I'm going to check if I do not have that element in my input, or if it's 0, apparently, as Farouk said. So I'm going to check, do I have an octopus at this AI and AJ? So do I have an octopus in my input at these coordinates? If I don't have an octopus at those coordinates, that means I'm probably in the corner of the map or on the left side of the map. Then I'm going to continue. That means I'm just going to go on to the next iteration in my loop here. And if I get past there, it means that I do have an octopus at those coordinates. So I'm going to check that octopus. I'm going to set octopus, so my new variable here, to that neighbor. So the A.I and A.J is going to capture the octopus at that location. So for the first row, it would be the octopus up and to the left. And now I'm checking. If that octopus's value is 0, I'm going to continue because I set my octopus to 0 at the very top of this loop. So that means if it's 0, that octopus has already flashed during this round. I want to ignore him. And if he has flashed, so if that's true, then I'm going to continue. So I'm going to skip ahead, check the next neighbor. So if we get down to the next one, it means that I have an octopus in that location and that octopus has not yet flashed. So I'm going to increment that octopus. And now, if that octopus is now greater than 8, that means that means that that octopus is going to flash. So I need to check his neighbors too. And so I just have a recursive function here, check neighbors, where it's when one octopus flashes, it's going to check all the neighbors. If any more octopuses flash, it's going to check their neighbors, and it will spread out until it's checked all of the neighbors or until the flashing stops.
Well done.
Cool.
And so I've used this similar approach to quite a few of the Advent of Code questions this year and last year. So I have a main loop and then a recursive function.
Yeah, makes sense.
All right. This one was a fun one, I thought.
I think that
the octopus, they look cute.
line 43
Yes.
might be already being checked by line 41, no?
Yeah,
Because-
that's what I'm thinking. It could possibly. I
But
don't
that's
think that
the
one.
problem I had.
Yeah, well, I'm still getting the correct answer, so it seems that that condition is already taken care of. So I could get rid of that line. Yeah, that's interesting. Yeah, I guess the way that my code was set up, it didn't really matter.
But in mine, it was skipping, so I had because I had to check the neighbors of 0 at least. That's why.
I think because of the way I structured my code, where I set that octopus to 0 right after it has flashed, but before checking its neighbors, I think that allowed me to ignore anything that's 0. Because if it is 0, I want to ignore it. I don't want it to do the rest of my code. So if it gets captured in this condition, then that's great. I want to ignore it. Yeah, all right. A lot of comments in here to help me explain it.
Okay.
All right, no more questions?
Because in mine, I think its neighbor can be 0, might be 0, but it might not have flashed. So I had to increment it, but I was not incrementing it. So that's why, yeah.
Because I'm doing my initial increment first before I check any octopus. So I'm incrementing everything at the beginning of the step, and then I'm checking my neighbors. So because of that, any octopus that is 0 means that it has already flashed.
Yeah, I think that's part actually different than mine. In mine, I am sequentially like incrementing and checking neighbors and then continuing with mine.
Yeah, I know it. I have to have extra loops in here in order to do that, but it made it a lot cleaner to work with.
Yeah.
To not have to worry about things happening at the same time. It was much easier for me to just increment everything and then loop again to check the neighbors.
Like
instead of trying to account for it all at the same time, that would have been it gets a lot more complex when you do that.
Okay.
All right, let's see how Alex did it.
All right, mine is kind of a amalgam of what you guys had already done. Let me see if I can find it. I think it's this one, I believe. Yeah, except it's 11, not 10. I will zoom in because I know it's a little small for you guys. Get rid of the noise. All right, so for today, for day 11, I also just put it right into my normal code instead of trying to do a read in on a file. So actually don't even need the first line. But anyways, so my approach is similar, probably more similar to Scott's approach in that I break things out into discrete steps. And so I think it'll be, well, let's get this out of the way. So the data is just in there. And then I just create the data structure that I usually create. It's just going to be a vector of numbers. So an array of numbers. And this is the thing that does all that nonsense. But I think, so down here is essentially what drives this whole thing. So, and I thought I put comments in here, so let me refresh this really quick so to see if the comments come back in. But essentially, I have a part in the bottom that drives, and I try to put things into more functions on this stage just to keep it a little bit more readable. And so the first step I do is I increment everything by 1. Yeah, I thought I had a little comment here before, but anyways, so first thing I do is I increment everything by 1. And so that function being up here is just, it's a simple function. I have two versions. I tried doing a mutable iterator as well as just a regular for loop. I don't know. Whatever one's more readable for you, they do the same thing.
Just a loop within a loop, right?
Yeah, it's just a loop within a loop.
And increment.
Yeah. But there's side effects, so you have to use a mutable iterator. But anyways, going down, and then after everything has been incremented by 1, then I find that which ones have flashed, right? And so find flashes is here, where find flashes will essentially go through my entire grid, and it'll check each point on the grid. And so calling checkpoint to see whether or not something is greater than 9. Now, one thing I'll point out that's a little bit different from my approach to you guys is I didn't reset back to 0 until it's finished. So it can go beyond 9. It can go to 11, 12, 13, 14. I didn't care. Okay. So I knew that as long as it's above 9, I can account for it at the end to see what it flashed and whatnot. So I didn't try to do that accounting at the same time. So on each of these, let's see, if on this particular point, if the number is above 9, and it's not already been flashed in the past, that's on this one, then I add it to a list that I need to flash these. Or actually, points flashed. So, but yeah, so this is a list of things that are going to be flashed in this round. And you'll see why in a little bit later. And then I go and check its neighbors. So check the row above. And then let's see, if the row above, I increment the row above by 1, and then I run a checkpoint on that one as well to see, again, is it above 9? And has it already been flashed or not? If not, then it will flash, and then it checks its neighbors. And so that's the recursion on it. And checking the ones right above and to the left, the one right above it, also check it. And also on the one on the right, advance it by 1 and also check it. Remember, my checking is just whether or not it gets pushed into this vector of things to flash. Same thing in the same row, same thing on the row below. So it checks all its neighbors recursively to see, it increments all its neighbors and sees, do I need to flash this or not at some point in the future? The numbers, remember, go beyond 9, it just keeps going. And so at the end of this, I should have, let's see, as you go through, I should have an entire data structure, points flashed, which contains all the things I need to flash on this particular move or round, whatever. And then, see, where do I account for that afterwards? Because I return this, points flash? No, I don't return this. So at some point, I need to account for it. Where do I do my counting? I don't remember. Let's just keep going. Maybe it'll come back to me. So after it finds all the flashes, it mutates input. Points flash. Mutable. Well, I don't do anything with it. That's interesting. Anyways, after the find, then I look at the total flashes, and the total flashes is a result from the reset. And the reset will get the vector. The reset will take the vector, and it just goes through each one of the vectors, see if any of these points are greater than 9. And if they are, then I reset it back to 0, and I just count number 1 of flashes. So it just goes through and does the accounting. Is anything greater than 9? then okay, that's a flash, and I reset it back to 0. That's about it.
All right.
Now the find flashes, I have a grid, the checkpoint after it's done. Oh, because I'm manipulating the grid itself. So the checkpoint is just to see, the points flash is just to see whether or not it needs to be added to the points flash or not. So this is just a way of blocking re-adding to things that are already going to be flashed. Which, come to think of it, I might not need. I might not even need this, since I'm just accounting to see which ones are greater than 9 and not really having to. I'm cutting them everything out in steps. So first step, turn everything, or increment everything by 1. Second step, go through the entire grid and find each one of them that needs to be upgraded or flashed. And then the last thing that I do is collect everything that's greater than 9, set it to 0, up my flash counter. That's it.
I like how yours is really structured, like step by step.
Yeah, and some of it was just also me trying to like think of what I need
Logically
to do.
process it.
Yeah. And so for each step, it's basically increment by 1, find which ones have flashed and update all its neighbors as well. So all the numbers proliferate. And then I do my accounting to see which ones are greater than 9 and reset them to 0 and up my numbers.
All right.
And I do that 100 times.
Woohoo.
And I found out recently, since 10 days ago, I could have done this as well. But anyway, little things we learn along the way.
What does it mean, the for underscore from the beginning?
Oh, this?
Yeah.
It means I need a variable there, but I'm never going to use it. So it's a throwaway variable.
Oh.
Okay.
Okay.
Yeah, I wanted a for loop that stays within a particular bounds. And the for loop format requires me to put a variable in here to track the value that I'd never use it. So the underscore is a throwaway.
Okay.
All right.
So that's it. All right, let's go to part B.
Yeah, part 2. Let's review the question then.
Yeah, so that was part 1. Part 2. Seems individual flashes aren't bright enough to navigate. However, you might have a better option. The flashes seem to be synchronizing. In the example above, the first time all octopuses flash simultaneously is step 195. So you see step 193, they're all 7s. Everything increments by 1, so all 8s in the corners go to 9s and 6s, and then that's
He's
the step
surrounded by
afterwards.
9.
The 9 burst, and each 9 contributes 1 to the corner, so that turns into a 9, but that bursts over this corner, and that contributes that one. Everything cascades in.
Everything.
Oh,
Yeah.
So that's just a giant bright light that you can now navigate by.
Exactly, 195.
All right.
And so
Yeah,
what is the
and
first
which
step
step?
during which all octopuses in your puzzle flash?
All right. Interesting. Your answer was 502. I believe that's the same answer I had too.
Oh, yeah? Maybe we have the same problem sets. Was your first
Yeah, it
set
could be.
1713?
Yes. We had the same one.
All right.
Interesting. I think that's the first time that's happened. Or first time we've noticed it happen.
Yeah. So, excuse me. So on this one, the answer set, part B, pretty similar to part A. The top is pretty much all the same. The steps, the flash points, all the same. The find flash is all the same. The reset is all the same. The only thing with the reset, oh no, I even have the more than 9. I have the vestiges of the last one, so that's all the same. So the only thing that changes is I added this. If total flashes equals 100. I thought about maybe just going through all of them, creating a new structure to, or checking a new function. I don't even know if I read the, oh, I did create the function to see whether or not they're all zeros. To see whether or not they all flashed, but figured might as well just count the number of flashes on each step
Yeah, it's nice that it's a small 10 by 10 grid, so we know there's only 100 octopuses.
Right.
Yeah, and so as soon as it hits 100, I break, and I added one more variable to count the number of cycles that go through my loop. It's no longer a while loop that's bound to 100. Now it's just an endless loop that's going to be broken out as soon as total flashes equals 100.
Yeah.
Then all I need to do is keep account of how many cycles went through the loop and then print it out afterwards.
All right. Yeah, it was not too much extra code from part one.
Yeah,
Nice.
Can I share mine then, since my part two is really similar?
sure.
Part one, here's my part two. Yeah, so just like Alex's, most of my code is almost the exact same as part one. At the very top, all of this is exactly the same. Down here, I just have a few differences. So in my main for loop here, instead of running 100 times, I just took out the stop condition because I'm going to break out when I get to my count of 100. Stupid pop-ups keep coming up. So I just removed that second condition. You can do that in JavaScript, but you still need to add the semicolon. So, and now new for part two also is I'm resetting my counter to 0 after each step, because I want not the total number of Dumbo octopuses that has flashed, but I want the total number for that step to be 100. And then, yeah, everything else is exactly the same. I'm going to increment all my octopuses. I'm going to check their neighbors and flash them. And then if my total count is 100 for that step, that means they have all flashed. So I'm going to log that step and break. And that ended up with the exact same answer that Alex had. Yeah, I got 502. Did you get the same result, Farouk?
No, mine was 268,
Oh, okay.
almost half.
Yeah, I like that. This was one of the lucky questions where my part one made it really easy to do part two. That doesn't usually happen.
Yeah. Part two was not that different, right?
Yeah. Any questions?
Nope. Good.
All right, pretty much the exact same extra code that Alex added.
Oh, my extra code is quite different.
Oh, let's see it.
As usual, my top, like the first half for part two, is similar approach, like the same code basically. But what I'm doing is after I have flashed all the neighbors and all the elements higher than 9, before I increment my step, I'm looping through every line in my graph or in my map. And in that line, I'm checking if every element has flashed. So the condition is in coordinates 0, 0. So I'm checking if every element is equal to the initial element on my like 0, 0 index element on my graph. So in order for all of them to have flashed, they all needs to be equal to 0. But I think I'm just checking if they are equal to the really first index element. And I'm going line by one. So if any of the lines do not contain the same elements, I break out of my loop. So I set my all same to false. And here I will break my loop, my outer loop, I think.
Yeah.
I have a for loop here, and my for loop has in the first one, it was 100 steps, but for the part two, I'm just slowly incrementing my steps. So I checked with 200 and 4 and 500. So it's at 500 until it reaches the point where all the elements flash at once. The number kept incrementing the length. So if it's not equal, all same is set to false. But by the end of this loop, if all same is true, I'm returning my step number and breaking out of my loop.
Would yours also return if all of the Dumbo octopuses happened to be the same number that wasn't 0? If somehow they were all 5s, for example,
Yes.
that would trigger your final condition, right?
Yeah. But I think we do not have that case.
Yeah, it didn't happen.
Well, it would only happen if they all flashed.
Yeah.
Right. If they
Yeah,
all
they just
flashed
wanna
and
be-
then went up to 1, and then they all went up to 2, and they all went up to 3. So
Oh, yeah.
Well, not necessarily. The corner ones would be a little bit different though, because they don't have as many neighbors.
but he's just checking on the first one to make sure every element is the same as the corner element.
Uh,
So it's essentially checking to make sure that every element is the same.
yeah, which only happens when they're all after they've all flashed.
Right.
All right, looks good.
Cool.
I think I should have implemented to use while loop here, but I wonder how I opted in for for loop because this logic is for while loop. But I seem to have stayed with the for loop, and because this loop is running running until the end every time.
Right.
But basically, yeah, that's my approach.
Cool. Cool.
All right, Dumbo octopuses.
Yeah.
Okay.
Let's call that here. It's already like 1:20. So and we'll plan for the next video. We'll go over 2 questions since we finished we finished the questions, so we'll go over 2 answers. So for the next one, we'll go over 11 or 12 and 13.
Okay.
But this I guess now puts us pretty much halfway through the answers, right? Well, not quite yet. Maybe next session on Wednesday will put us halfway through the answers, right? So anyhow, any other comments before I close it up?
No.
Good job. They're getting harder.
Yeah,
Yeah.
they're getting
Right.
more involved, I guess, in the sense that you have to think about it. I mean, the coding, I think, is whatever it is, but I noticed that by around point about day 11, my Haskell's Rust is
Right.
becoming a little bit more automatic, where I don't have to like look up every word before I
Oh.
type it.
That's good.
So it took a while, but there's still a lot I don't understand. So, but yeah, cool. And we'll see you guys again on Wednesday.
All right, take care. Happy coding.
All right.
Take
Bye-bye.